Imagine a tidy room, clothes folded, books stacked. Now imagine the same room after a week of living. Which state feels more likely if you close your eyes and open them later? That gut feeling disorder tends to increase is the everyday shadow of a deep physical law. Entropy is the count of ways the world can be arranged under the hood without changing what we can measure at a grand level. It is the number of secret microscopic stories that hide behind the same visible scene. When there are many stories, we say entropy is high. When there are few, entropy is low. In thermodynamics, we usually talk about macroscopic variables, energy, volume, particle number. Those are the privileged knobs we can measure and hold fixed. Given those knobs, entropy is a number, how many microscopic arrangements fit the bill. Fix the energy, the volume, and the number of particles, and you get a single thermodynamic entropy for that equilibrium state. Let's make this concrete. Picture 10 coins on a table, each heads or tails. If the grand observation or grand description is exactly one head, there are 10 ways to place that head. If the description is 5 heads and 5 tails, there are many more ways. The latter macrostate has higher entropy because it can be realized in many more microscopic ways. For a gas in a box, the microstates are the positions and momenta of all the molecules. We do not measure those. We measure pressure, temperature, volume. Those are our coarse-grained descriptions or grand descriptions. Entropy counts. How many microscopic arrangements match those coarse measurements? That's why thermodynamic entropy feels objective. It's tied to the natural, physically meaningful variables we use to describe bulk matter. And because the number of microstates typically grows with energy, a hotter box of gas usually has higher entropy than a colder one. When we compare them using the same thermodynamic coarse graining, that ordering is robust. It's not an accident of math. It's a consequence of how energy spreads across many microscopic degrees of freedom. Now slide from coins in gas to the quantum world. A single quantum system can be in a pure state, a coherent superposition of many possibilities. Mathematically, a pure state has 0 von Neumann entropy. That sounds odd. How can a state that looks messy, a superposition of many outcomes, have 0 entropy? The key is that quantum entropy measures mixedness, not the number of terms in a superposition. A pure superposition is complete knowledge of the global quantum state. Entropy becomes non-zero when we lose access to information. When we ignore degrees of freedom, such as when the system becomes entangled with an environment and we trace out that environment, that operation, tracing out, is the quantum version of coarse graining. So both thermodynamic and quantum entropy arise from the same conceptual move. You choose which details to keep and which to ignore. The difference is emphasis. Thermodynamics privileges macroscopic, conserved quantities like energy. Quantum theory reminds us that the universe, at the smallest scale, can be pure and reversible. Entropy appears when we coarse grain or when subsystems become entangled with inaccessible degrees of freedom. The second law of thermodynamics says that for an isolated system, entropy tends to increase. If you start with a low entropy arrangement, say all the gas in one half of a box, the system will, with overwhelming probability, evolve toward the equilibrium macrostate, where the gas is spread evenly, and entropy is maximal for the fixed energy, volume, and particle number. This is not a mystical decree written into the microscopic laws. Newton's equations and quantum evolution are time reversible. The arrow of time emerges because low entropy states are rare. When you coarse grain, the number of microstates compatible with, say, spread out gas dwarfs the number compatible with, say, all gas on the left. So the system wanders into the larger set and stays there, except for astronomically improbable fluctuations. Those fluctuations are real. In a small system or over short times, entropy can dip. But for macroscopic systems, the dips are so unlikely that we treat the approach to equilibrium as effectively monotonic. That's why your coffee cools and never spontaneously reheats. Now imagine waiting not minutes or years, but time so vast that even the rarest events eventually happen. In a universe that sits near equilibrium for unimaginably long stretches, random fluctuations can assemble unlikely structures. Among those structures, some thinkers have imagined, could be a brain, a configuration that, for a fleeting moment, has the right pattern of matter and activity to host conscious experience and memories, that hypothetical creature is called a Boltzmann brain. It is a brain that pops into being like a perfect photograph, developing in an instant. Every synapse, every firing pattern arranged by chance, and with it comes a full archive of memories. Childhood summers, a first kiss, the taste of coffee, a lifetime of friends, and failures. None of it has a causal past. The memories are not records of events that actually happened, but perfectly consistent pieces of information assembled by a fluctuation. From the inside, the world looks utterly real, yet outside that skull, there is no history to back it up, only cold, featureless, heat death. The paradox is unsettling. If the universe is eternal and dominated by high entropy states, then the probability of a single brain fluctuating into existence might, in some calculations, exceed the probability of an ordinary evolution of a real universe from a low entropy starting point. If that were true, most observers would be Boltzmann brains, and our own memories and observations would be suspect. So the question is, are we Boltzmann brains? Let's not sweep the Boltzmann brain idea under the rug. Instead, let's sit with it and let it do its job. Pry open assumptions we usually take for granted. If a cosmological model genuinely predicts that most observers are fleeting, randomly assembled brains with false memories, then that model forces us to confront what we mean by reality, evidence, and explanation. It's not merely a technical nuisance. It's a philosophical scalpel. First, there's an epistemic sting. A Boltzmann brain could have a full set of memories and sensory impressions that are internally coherent, but causally disconnected from an external past. If our evidence for the past is just the present configuration of our brains and records, how do we rule out the hypothesis that those records are random artifacts? This is not a new skeptical challenge dressed in physics clothes. It's the old problem of radical doubt reframed by statistical mechanics and cosmology. Second, there's the measure problem. To decide whether Boltzmann brains dominate, we need a rule for counting observers across enormous or infinite spacetime. Different counting rules give different answers. For example, by one calculation, a Boltzmann brain would appear as a quantum fluctuation in the vacuum after a time interval of 10 to the power of 10 to the power of 50 years. But such a calculation depends on many assumptions. You change those assumptions, the number will change a lot. That means the question of, are we Boltzmann brains, is entangled with how we assign probabilities in cosmology. That's uncomfortable because it makes a seemingly empirical question depend on a partly philosophical choice about how to weigh possibilities. Third, Therese, the methodological response. One route is pragmatic. Prefer theories that make our observations reliable and predictive. If a model implies that most observers are deluded Boltzmann brains, it undermines the very practice of science. So we treat that as a strike against the model. But that move is not purely empirical. It's a meta-scientific constraint. We demand that our theories preserve the trustworthiness of evidence. That's defensible, but it's also a philosophical stance about what a scientific theory must do. So let's be open-minded without being paralyzed. The Boltzmann brain possibility is a natural extension of the concept of entropy in thermodynamics. Entropy is the bridge between microscopic possibility and the macroscopic stories we tell about the world. It counts how many hidden arrangements fit the facts we measure, and it explains why systems march toward the overwhelmingly probable equilibrium. That same counting, pushed to its logical extreme, gives us the Boltzmann brain thought experiment. It is a legitimate philosophical probe, a way to test the coherence of cosmological theories and our standards for scientific explanation. Whether it ultimately upends our picture of reality or simply helps us discard bad models, it performs a valuable role. It makes us ask carefully and honestly what we mean when we say we know the past.